Hello, I wanted to give one last video to talk about the variety of other types of statistical inference hypothesis tests that are available to us. And also just to talk a little bit more about, in general, the practice of statistical inference. So what are the tests that are available? What questions can we ask that we haven't already covered? So far, we've been asking for the difference between the means of two populations. If we had the difference between more than two populations, three or more populations, we would have to perform a one-way ANOVA, or one-way analysis of variance. So in here, the null hypothesis is that the means of every single group is exactly the same. And the alternative now is that at least one of those groups has a different population mean. So if this comes out as significant, you have more work to do to find out which group it was. This deals with means, so it's a parametric test. So one of the main assumptions here is that all our populations are normally distributed. So if we are not normally distributed, what can we do? The non-parametric equivalent of this is a Kruskal-Wallis test. The null hypothesis is that we have a lot of groups and all their medians are equal, and the alternative hypothesis is that at least one group has a different population median. So far we've been comparing means and medians. There are other statistics we can compare. So we can compare proportions. So if we had one sample and we wanted to compare the proportion of things in that sample to a specific proportion. So for example, we wanted to know is support for the Queen equal to 80% or not? Then we'd take a sample of the population of Britain, and we'd ask everyone, do you support the Queen or not? And we'd get a lot of yes or no, so we'd get a proportion of people in that sample who support the Queen. So then we'd ask, the null hypothesis would be, is that proportion equal to a given value, 80%? And the alternative would be it's less than, not equal to, or greater than that proportion. The way this works is really neat. So the way this works is that out of our specified proportion, our observed proportion, and the number of things in our sample, so P, P star, and N, we can create a new statistic, Z, which follows a standard normal distribution. So from this, we can just look at normal tables to find our p-values. So that's really neat. What if rather than having one population, we had two populations, and now we wanted to compare the proportion of one population to the other? So for example, what if we just wanted to know, is support for the Queen different in Wales to it is in England? So our null hypothesis would be, is the proportion of people in Wales who support the Queen equal to the proportion of the people in England who support the Queen? And the alternative would be that the proportion in Wales is less than, not equal to, or greater than the proportion in England. So we're not comparing to a specific number now. Again, the way we calculate this is really neat. It takes a little bit more working now. So now we've got P1, P2, N1 and N2 to two different sample sizes. But this thing then, Z, follows a standard normal distribution. We've talked a bit about correlation before. When you are calculating correlation, one of the measures is called a Pearson correlation. So I'm not going to show you how to calculate it, you can look that up. But if you are going to calculate a correlation on a sample, then you need to perform a hypothesis test. So a Pearson correlation, as we've said before, lies between -1 and 1. Correlation of -1 would be perfect negative, +1 would be perfect positive, and 0 would be no correlation. But if we're doing this on a sample, we want to ask, is the correlation of the population equal to 0? That's our null hypothesis. Or our alternative hypothesis that the correlation of the population is less than, not equal to, or greater than 0. The Pearson correlation is a parametric test. There's a lot of assumptions we need to follow. So one of the assumptions is that we're only looking at linear relationships. The other assumption is that the data is homoscedastic, which means that for every x value, we have the same variance in the y. But if our variance changes with the x, or we think we've got a correlation which isn't linear, we can use a non-parametric version of this, which is the Spearman rank correlation. And again, this is interpreted the same between -1 and +1 for negative to positive correlation. And again, if we're doing this on a sample, we need to perform a hypothesis test before we can infer the correlation for the population. When you do correlations with statistical software, it will pop out a p-value for you, and you need to know how to interpret that, and it's these tests. Related to correlation is linear regression. So linear regression is when we have two continuous variables that we think are correlated, and we draw a best fit line. That best fit line does more than just show us visually that there's a correlation. We can actually use it to predict. So there we can say, well, for a height value of 60, we'd expect a weight of around 62, where that line is. So that's useful. And remember back to your last module, what is a straight line? It has an equation. So we can write down that the weight, or the y, is equal to an intercept, beta naught, plus a gradient, beta 1, multiplied by the height. So we can work out what the weight would be from a given height. When you do this on a computer, it'll pop out beta naught and beta 1 for you, but it'll also pop out p-values for these. Because if you're doing this on a sample, you want to know, does that best fit line apply to the population? So for every parameter in your line, you would have a hypothesis test, the null hypothesis being that that parameter is 0, and the alternative is that it is less than, not equal to, or greater than 0. For all our t-tests, normality was an important assumption. We can check whether the data is normally distributed. So if you've got a sample and we want to know if the population is normally distributed, we have some normality tests. And there's lots and lots of these normality tests. Two that I'm going to point out to you here. One is called the Shapiro-Wilk test. That works really well if you have less than 50 observations, roughly. And another one is the Kolmogorov-Smirnov test, which works really well if you've got more than 50 observations. And there we are testing the null hypothesis is that it is normally distributed. The alternative is that it's not normally distributed. So that is the kind of variety of tests on offer. There's a lot more. I just want to talk about some of the more popular ones. I'd like to talk now about the practice of statistical inference and maybe talk about some misunderstandings. Significance does not mean a big difference. Significance doesn't mean an important difference. Okay? Significance just means not a fluke. It's not any relationship we are seeing is not just down to how you've sampled. It's not a fluke. Significance just means that we can be confident that whatever relationship you're testing for appears in the population. It doesn't mean big and it doesn't mean important. Another important thing to think about is that we're only testing very, very precise things. This is something that could genuinely happen. We could be testing that the null hypothesis is that the population mean is equal to 8 kilograms, and we could have the alternative hypothesis is that it's not equal to 8 kilograms. We could get a very, very, very small p-value, which indicates that that null hypothesis is probably wrong. So we resoundingly reject that null hypothesis. Whereas in reality, the population mean was 8.01 kilograms. 8.01 kilograms is not 8 kilograms, which is why we rejected it. Significance doesn't mean big and important, and we are only comparing to that very precise null hypothesis. You might see the word p-hacking around the place, and this is really, really bad practice when it comes to statistical inference. Another related word is data dredging. Again, this is bad practice. A lot of this might be just misunderstandings, but there are some just fraudulent and lying activity as well. So one of those activities is performing many, many tests and only reporting significant results. Now, if you're going to perform a lot of tests or a lot of experiments to show, does eating toast cause cancer? most of your experiments show that it doesn't, but then you happen to have one sample which shows that yes, we cannot reject the null hypothesis that toast doesn't cause cancer, and you only report that. That's really misleading, that's actually lying, and you shouldn't be doing that. A common misunderstanding, which when you're writing up about your statistical inferences you need to avoid, is flipping the condition of the p-value. So remember, what is a p-value? It's the probability of seeing what you've seen given that the null hypothesis is true. It is not the probability that the null hypothesis is true given that you've seen what you've seen. And that's a very common misunderstanding. So if you get a p-value of 0.04, that doesn't mean there's a 4% chance of your null hypothesis being true. No. Another really bad practice is when you're performing these hypotheses that you're omitting data just so you gain some significance. That is essentially you're hand picking a sample there so that you get those extreme results, and that is again just lying. But here's one that might not be so obvious. Validating your hypothesis on the same data that you devised your hypothesis. So what does that mean? That means I've gone out and collected a load of data. I've done a load of plots just to see what it looks like, and I can see, oh, these two variables seems to be a relationship between them. And then on that very same data, I perform a hypothesis to check if there's a relationship between them. What am I doing there? Why is that wrong? Well, there's a few reasons. So first of all, when you do exploratory data analysis, you're going to be checking loads and loads of different relationships. Think back to the law of large numbers. The more checks you do, the more different variables you look at for relationships, the more relationships you're going to find, because you're going to find extreme results. So there's that, that's bad. But why this particular thing? Why validating your hypothesis on the same data you found it? Well, you're changing the definition of the p-value there. The p-value is the probability of seeing what you've seen given the null hypothesis. But if you already know that it looks like there's a relationship on that data, what your p-value then says is, what's the probability of seeing what I'm seeing given the null hypothesis and that I have already seen a relationship? And that changes the p-value. So you shouldn't be doing this. Best practice would be go out and collect some data, perform loads of exploratory analysis on it and find these relationships that you think might exist. But rather than draw any conclusions from that, just note them down. Note down what relationship you think exist. And there's going to be a lot because you've going to done a lot of different checks, and the law of large numbers says some of those are going to look like relationships, okay? And then put that data to one side, go out and collect some more data, and on that new data, check for the hypotheses you wrote down. A nice analogy of this is something called the Texas sharpshooter fallacy, and this really shows how silly you're being when you do this. So the story goes that a rancher in Texas picks up a gun and starts randomly shooting the back wall of his barn, just randomly shoots everywhere. After he's finished shooting, he considers what he shot at and then hangs up a target and says, I am the best sharpshooter there is in Texas. Now clearly that's silly, but that's essentially what you're doing when you're validating hypotheses on the data you found those relationships in the first place. You found the relationships, which is where are all those gun holes. Then you're checking a hypothesis, which is your target. You're checking whether those gun holes hit the target, where you're the person who hung the target up. So this is a prime example of p-hacking, and this is really, really bad practice. You shouldn't do this. One way of getting over this, and a lot of academic journals are starting to do this, especially in stuff like biology and chemistry, is called pre-registration. And what does that mean? Before you go out and collect your data, you've got an agreement with an academic journal that they will publish your work, and they will publish your work based on this set of hypotheses that you're going to have to test. But you haven't collected your data yet. So the journal already knows what hypotheses you're going to go check. Then you go collect your data and check those hypotheses, and whether it's significant or not, they will publish it. And that's really good practice, because quite often survivorship bias, we don't publish insignificant results, and then we don't know they're insignificant results. So we're moving in the right direction in the science world.